So first, thank you to the organizers for having me here. I think we can all agree that it has been a very condensed, very action-packed last 2 days. So I think it's now Thursday. We need to relax a little bit. So I'm going to only show you pictures and as minimum equations as possible. OK? So the title of my talk is an electronic de-Laval nozzle. Sounds very fancy. I'll try to explain what this is to you. The people who actually did the work are shown here in this picture. So the person you should really pay attention to is Tatiana Webb. I'm going to talk about some scanning measurements. And Tatiana is really this fantastic postdoc, the postdoc that everybody wishes that one had many, many of these. She has installed this instrument. This is a wet fridge from Atocube. So I'm told that Atocube does not sell this wet fridge anymore. So ours is only 2 or 3 years old. But maybe it's an antique piece, so we can charge admission fees if you come to see it from now on. So Tatiana has helped in her scan probe measurements by another postdoc, Itai, who's very young and enthusiastic. The sample that I'm going to talk about, this particular de-Laval nozzle, is made by another postdoc, Johannes, who also came up with some of the crucial ideas for this project. And Johannes is helped in his fabrication by Yinji, who's very quiet but very efficient graduate student. And this particular instrument, which lives in my lab, was actually paid for by 3 of us at Columbia. We like to do things as a team. So these are my 2 colleagues, Corey Dean and Dmitry Basov, together with me. OK, so where does this story begin? So the story begins with electron hydrodynamics. And for those of you who have been following this field, there have been a number of demonstrations in the past few years where essentially people have shown that it's possible to reach a regime in 2D materials mostly, where the electrons that are flowing through the sample behave, instead of normal electrons, they behave like water. So in other words, the most dominant scattering channel is electron-electron scattering, which is momentum conserving. So I've also been following this field with a lot of interest and seeing all of these papers and envying some of them. But one question in my mind is, how am I going to make some money out of this? OK? So the first step to making some money is to have some sort of device where the fact that the electrons are hydrodynamic has some consequence for the device. And this is what I'm going to tell you about in the context of this de-Laval nozzle. OK, so if you go to Google and you put in de-Laval nozzle, the first thing you'll see is a rocket engine. So let me explain to you what this de-Laval nozzle is and how it works. So this is a rocket engine lying here on its side. And imagine you set the propellant inside the rocket on fire. Then what happens is, at the moment where the propellant enters into a gas form, the velocity of the propellant is actually below the speed of sound. It's a very hot gas. So as it comes out through the nozzle, this gas starts to cool. And as it cools, it expands. So this is something very familiar to those of us who do cryogenics. This is the so-called Joule-Thomson effect. And as it expands, the velocity of the gas actually goes above the speed of sound. So it goes above Mach 1 as it comes out through the bottom of this nozzle. And if the conditions are just right, so what do I mean by just right? When the gas comes out from the nozzle, the gas has to be going in a convergent direction, so it comes and bashes on top of itself. If it does this, then at the point where that happens, there is a shock wave that's created. And what is this shock wave? The shock wave is a location in space where the velocity goes from above the speed of sound to abruptly below the speed of sound. Okay? Something that you're probably much more familiar with is a very analogous thing that happens when anytime you flow water in your sink. I'm sure all of you have seen this. So this is a different but very similar phenomenon. So here the water picks up velocity as it drops from your tap. It hits the sink. And when it hits the sink, it has a high velocity. And it goes out in this almost laminar flow that looks like this. And then it goes out to a particular location. And at this particular location, there is a hydraulic jump. So this thing is called a hydraulic jump. And here, the velocity of the water goes from a high velocity to a low velocity. And that velocity, that change in the kinetic energy, is converted to potential energy at this particular location. And so electrons pile up at this particular location, and there's a hydraulic jump. OK? About 5 years ago, there was this very nice paper on the archive which told us how to do this in the context of electrons. This paper has a grand total, I looked yesterday, of 1 citation, but it's still an excellent, excellent paper. And so what this paper tells us is how one should do this in the context of electrons. And what they say is make a nozzle. Nozzle looks like this. And adjust the current that is flowing through this nozzle into such a situation that when the current is entering into the nozzle, the velocity of the electrons is a little less than the sound velocity. Then the electrons reach the middle of the nozzle. This is the throat of the nozzle. And at this point, they hit the critical velocity. This is called the choke point, where the velocity reaches Mach 1, the speed of electronic sound. And after it crosses through the throat of this nozzle, the electrons then expand. There's a Joule-Thomson expansion, where the velocity of the electrons is greater than the speed of sound, until somewhere beyond the throat, there is a shock wave front that is formed, where the velocity goes from above the speed of sound to below the speed of sound. And since we are talking about electrons here, what would happen here, if you imagine electrons piling up, the electric potential or the electric potential energy would pile up in this particular sample. Okay? So that's what it is. And they have some nice pictures here for how the velocity profile would look like going through the nozzle. So if you have subsonic flow, then the velocity just increases as you enter the nozzle and then decreases. So this is just Bernoulli principle for the pressure. And if you enter into this supersonic flow regime, then you cross the speed of sound as you go through the nozzle, and then there's a shock wave where there's a sudden drop in the velocity of the electron. OK, so which is the right material if you want to do this kind of experiment? One obvious candidate is monolayer graphene, but monolayer graphene turns out not to be the best choice for this particular experiment, because the velocity of sound, which for an electron is the slope of E versus K, is a constant. It's a Dirac dispersion. But on the other hand, if you take bilayer graphene has a quadratic or nearly quadratic dispersion. And so the speed of the electronic sound of bilayer graphene, if it's a perfectly quadratic dispersion, will go exactly to 0 when the density is 0. And if you're at relatively low density, this speed of sound for bilayer graphene is small. Okay? OK, very good. So here is a device. So this is a device which was made by Johannes. And Johannes came to us, where the story starts, is Johannes came to us with this curve. This curve is the differential resistance as a function of current. All of us do this, who do transport measurements. And he came and he showed us this particular curve. And he showed us this place of the red arrow and said, see, there's a shock wave. And I'm a scanning guy. And I was like, come on, right? How do I know this is a shock wave? So what he said is that there are various checks one can do to see that this is really a phenomenon associated with this kind of shock wave effect. So one thing you can do is you can change the density of the electrons by applying some gate voltage. And as you change the density of the electrons, you change the sound velocity. So as you change the sound velocity, the location where the shock wave happens, the current at which it happens also changes. And he was able to show that that happens in a reasonable fashion. It happens up here. He also did the same experiment in monolayer graphene, the same nozzle. There was no such effect. He took, instead of a nozzle, he took a Hall bar, regular Hall bar geometry for bilayer graphene, showed that this effect did not exist. And finally, and perhaps most importantly, if you apply a fairly small magnetic field, you mess up the electrons because they're not going straight anymore. And if you do that, also this effect disappears. Okay, so he had some reasonable evidence to say that this is actually the shock wave phenomenon. But we want to try to do something a little better. And so what he was telling us, this was his theory, was if I have a source and a drain, and I have electrons going from one side to the other, then the electrons are getting, the electrons are getting compressed. Their velocity is getting higher as it goes through here. And then as they come out here, they expand, and then there's a shock wave that's happening somewhere here, and there's a little bit of a potential jump that happens as it goes across this point. And I should say that this transport data, which to me already is not very impressive, when we asked him to reproduce it in a number of devices, usually this is like the best one that you can get. Usually it's a little bump that happens up there. Okay? So we would like to go in there and scan this sample and actually see if we can see any kind of this kind of potential effect. And so that's what we set out to do. And the way we do this experiment is a very standard technique for those of you who do AFM. This is called Kelvin probe force microscopy, For those of you who are not completely familiar with this, the basic idea is very simple. You have a tip and a sample, and the tip and a sample both are metallic, and they form a capacitor. And so there's an energy stored in this capacitor, which is 1/2 CV squared, where V is the potential difference between the tip and the sample. And the AFM is very good at detecting forces. And so when you look at a minimum of the force as a function of the bias applied to the tip, that force will be minimized when the electrostatic force is minimum, which happens precisely when the potential of the tip matches the potential of the sample. So that's a simple idea. And you can convert this into a scanning instrument. It's there pretty much in every AFM. So the experiment that we are going to do is we are going to flow a current in our sample, and then we are going to take our scanning tip, we are going to put it at different locations, we are going to do this KPFM measurement and just measure the local potential at every point on the surface. Okay? And of course, there are other ways of doing it, some of which are better and have other advantages and so on, but we had this instrument, so this is what we did. Okay, so let's start with the data. So here's the samples. Here's a AFM topography of the nozzle structure. And what we're going to do again is we're going to set up a current in this, and then I'm going to measure the potential. And so let me show you that. So this is the potential measured when there is a particular value of current. Here it's 1 milliamp of current that's flowing from one side to the other. And even though this picture looks very simple, I should warn you that this thing, at least in our system, this takes many, many hours to obtain this. And there are many troubles to this. There are the usual troubles anytime you have a tip, if you have junk and other sorts of things. But Tatiana also had to develop a nice sideband way of doing this, which made it feasible at all to get images like this. Okay, so this is the basic data that I'm going to show you. And what I'm going to show you is what these potential profiles look like at different values of current that's flowing through the device. Okay, so for the rest of the talk, these kinds of 2D images really take a long amount of time to take. So in order to simplify matters and speed up our life, what we do is we take the tip and move it along a line that goes exactly through the constriction. We actually average over some distance. It's on the order of a fraction of a micron. We average across in that direction. And what I'm plotting here at the end of the day is the potential of the tip as it goes from one side to the other while a current is flowing. And what you see in this basic image is that the potential is low. This is the drain side. The drain side is at low voltage. And so if you're close to the drain, the voltage is small, as you might expect. And as you go through the nozzle and go across to the other side, the potential rises and then becomes high as you go on the other side of the nozzle. No great surprise there. And this is, again, this is taken at one particular value of the gate voltage. Shown up here, this is not very illuminating as looked in this particular fashion, but what these are in this 2D map is a sequence of these kinds of lines taken for different values of the current, right? So, and I'm going to go through this data in some detail. So if I pick one particular line like this, that would correspond to a line like that. Okay, so now before we look at this in more detail, let's try to build up some intuition for what this kind of curve should look like. And let's start with a very simple approximation. I'm going to assume that this device is just a resistor. It's an ohmic resistor. And if it's an ohmic resistor, then as the electrons go from here to here, the cross-section is decreasing. And so if the cross-section is decreasing, the resistance per unit length is increasing as you go through this particular nozzle. And you can just use the shape of this nozzle and just use Ohm's law and figure out what the potential should do as you go from the drain side to the source side. And indeed, as you might expect, it has this particular S-shaped curve. So here, it's one value of resistance per unit length. Here, the resistance per unit length increases as you go through the nozzle, and then the resistance per unit length decreases as you go on the other side of the nozzle. All very simple. For those of you who have been paying attention, you might say, hold on just a minute. You told me something about hydrodynamics. Where's the hydrodynamics here? Right? I want to brush that under the carpet, because as it turns out, in this particular geometry, the difference between an ohmic profile and a hydrodynamic profile is a subtle thing. And this is something, to be honest, we are still working out. There are differences, but this is still something to be worked out. But this gives you a good intuition for what this potential profile should look like. Now, let me assume that we are in linear response. So I, as a function of V, just looks like a resistor. And let's say this potential profile is measured at one value of current, and I change the value of current. then what do I expect? If I look down here, if I go from this yellowish curve to this more orangish curve, then of course, if I change the current and decrease it, I expect this potential delta V to also decrease along with the current. But if I look at the differential resistance should not care about the actual value of current used if I'm in the linear response regime. That's the meaning of linear response. And so I can do this for a bunch of different currents. And I can get different curves like this. But then when I take dV/dy as a function of x, they should all line on top of each other. And this is the basic intuition that you need in order to understand the data. OK, so now let's get to the real data. So what I'm showing you here is one of these cuts. And this is done at some particular value of current, which I'm going to call low current here. This is 1 milliamp. This is the potential profile going across the constriction. And this is dV/dy for that same curve. And now I'm going to increase the current a little bit. So here I increase the current a little bit. And you see, indeed, delta V increased, as you might expect. And something happened up there to dV/dy, which we'll come back to later. Let me show a few more curves. I'm increasing the current, increasing the current, increasing the current, blah, blah, blah. I go up there, and I give you this whole sequence of curves. And there we go. OK, so some things look familiar from what I told you on the previous slide. This phenomenon generally looks sort of like ohmic, but some things also look different. For example, here, all these curves don't lie on top of each other. And so you might ask, what is this? So let me go back to the transport dV/dy curve. So the transport dV/dy curve is just what you do in transport. You just measure the voltage right across the device. And this is the transport dV/dy curve for this exact same device as a function of current. And what you see in transport is that there's a small region where the transport is linear, and then very quickly the transport becomes nonlinear. Right? And so nonlinear resistors means that the resistance curves for different values of current should not fall on each other. Right? But we can do a little better than this by looking at this carefully. You can see that for this particular region between 0 and 10 microns, and this 10 microns happens to be precisely where the middle of this constriction is, all of the curves do lie on top of each other. So everywhere up from the drain contact to the middle of the constriction, you are in linear response. The current the dV/dy is independent of voltage. Then there is this segment between 10 microns and 15 microns. That's this blue region here, where the current as a function of voltage is nonlinear. And so that's why these guys don't lie on top of each other. But what you can see beautifully from this scanning measurement is you can see where the nonlinearity in the device is located in space. Okay? And then finally, as you cross this 15 micron threshold, if you look at this carefully, you'll see all of these lines are parallel to each other. Right? And in this region, again, you're in linear response. The reason that these curves don't lie on top of each other is because you're looking at the accumulated voltage as you go from one side to the other. And so it's picked up some additional voltage in this region, which is different from current to current. But once it gets to this point, it's once again linear, and you are in linear response. OK, so beautiful. So this is already something very nice that the AFM has told us beyond the transport measurement. It has told us where in the device we have linear response and where in the device I have nonlinear response. And so now the only thing that's left for me to answer is, where is my shock wave? OK, so if you go to the transport measurement once again for this particular sample, that is the signature of the shock wave in the transport for this particular device. It's not, unfortunately, not as impressive a feature as in some other devices. It happens around 3 milliamps for this particular value of gate voltage. And so one should go to these curves and look around the same 3 milliamps, which is somewhere up here, and ask, do I see any feature in real space corresponding to this? And indeed, for those of you who have a sharp eye, you can look right there. So here's a zoom in of that, and you can see precisely just before it transitions from this nonlinear response to this linear response, you see some funkiness happening with the voltage. I would have loved this to be a discrete sharp step. Life is not as kind as that. But you can certainly see that there is something that happens here as it transitions from this nonlinear response to this linear response regime. And the current at which this happens is precisely the exact same current at which you see this in the overall transport measurement. We can do a little bit better than that. So what we can do is we can do this transport measurement by simply putting our tip at different locations and sweeping the current. And this is like doing a transport measurement with a voltage probe at different locations as you go through this nozzle. And if you're on this side of the nozzle where the shock wave is not expected, you don't see the effect of this shock wave, that's down here. But if you cross the location of the shock wave, then you always see the shock wave in transport. One last piece of information before I quit for the day. One of the important signatures in transport is as you change the density, you will change the location of the shock wave, the current in current. We see that this also has an effect in position. So if you measure the position of the shock wave at two different values of current, then you see that this value of this shock wave sort of changes. And right now, the folks are in the process of making a nice movie and finishing this up, but they have already a couple of more points to add to this. I should say that each of these is sort of like a week's worth of running, so it's not slow measurements. And there's a few other things that we need to do, which is to make sure that with magnetic field, I think they've done that already, but they need to confirm that with magnetic field, this thing goes away in the scanning. So that's all I had. So I hope you enjoyed this, and I'm happy to take any questions.
Shahal?
Thanks for the beautiful talk. What sets the position of the shock wave? Should it start at the nozzle and then go out? It looks like there is a certain given distance from the nozzle to some place where it happens.
Yeah, so I think the closest I can tell you, it's approximately set by roughly the width of the nozzle. Now, one of the tricky things versus ideal theory is you might have noticed that we're using fairly high voltages in order to make these things happen. So there's several volts. So one of the effects that is tricky is that there is some self-gating. That is, as you go from one side to the other, the fact that you're using this large bias is also giving you a gating effect. And so that's something we're trying to work with theory. But roughly, it's around the same size scale as the nozzle if you work out the numbers from the hydrodynamics. People, the nozzle is about 3 microns. This happens at around 5 microns in our sample. Yeah.
So is it because of this self-gating that you don't see on the other side of the negative bias? Right?
So if you apply, so you have to be careful about bias, switching bias or actually switching the leads. The two things are different. But indeed, we have seen that if you switch the leads, you can make it go to the other side. Yeah.
More questions?
Nice talk.
Thank you.
I was wondering if you expect some other signature, like in localized increase in temperature, or perhaps a mechanical shock that could be picked up by the FM cantilever as well.
Yeah, so absolutely. So in this picture, there is a Joule-Thomson expansion. So there should be a change in the temperature of the electrons as they go through the nozzle up to the shock wave. And this is indeed where we see the nonlinear response. That's kind of a signature of this. But I know that there's other ways where you can locally measure the temperature directly, and one should see this there, yeah. It should happen asymmetrically, so it should happen past the nozzle. Yeah.
Abhay, you showed the, one-dimensional cut. I'm here. Yeah, you cannot. Anyway. You showed the one-dimensional cut. How about the longitudinal, the profile? I mean, it's a two-dimensional scan, right? How about the other dimension? Is there any interesting feature you will see associated with this shock wave? Yeah,
so when we apply a magnetic field, we did this. And then you can see some focusing effects where the potential kind of builds up in some place. So there's old transport work from Corey on this focusing business. There's also only one nice AFM experiment from Bob Westervelt where also they've seen this focusing. And in this geometry, it's not ideal for focusing because of the nozzle geometry. But certainly when you apply magnetic fields, because the electrons start to bend, you'll have these kinds of responses. Yeah.
Thanks, Abhay. Maybe I missed this one. Earlier, the transport data you showed with a jump, is that a two-terminal measurements?
4-terminal.
Okay.
So what matters is that you put your voltage probes beyond the position of the shock wave. So if you put your voltage probes here, you will not see the shock wave. If you put your voltage probes out there, then you will see the shock wave.
Okay, that's why you have only one direction, one current, direct current, you see the jump. not reverse current.
That's correct.
Okay.
That's related to the self-gating, yeah.
Okay. And what temperature range you see this?
A good question. So this should happen over a very wide temperature range, but these measurements are actually done around 20 Kelvin. Again, there's a significant amount of heating, which, you know, the cryostat does not react that much to it, but I couldn't tell you exactly what the temperature of the sample is.
Last question.
So if you were to make the device smaller such that hydrodynamic or ballistic effects were more prominent, how would your picture change?
So certainly, okay, I didn't talk about this, but in the same device, you can also see ballistic effects when you're at very, very low current. So then what this thing looks like it's ballistic to this point, and then there's sort of an impedance at this point, and then, so there's two different chemical potentials on this side. Now, I think what you want to be is you want to be in a limit where the size of the wave packets is much smaller than the nozzle. Right? And that's really what you want. And the rest of it really doesn't matter.